It's going to be high level. I apologize, but I hope you get something out of it. So yeah, at CSCS, we've long been looking at essentially the C++ standardization process in terms of executors in the past. Nowadays, it's called std execution, and it's actually here. I'm going to give you a brief overview. Feel free to come up to me afterwards if you want more details, and then talk about a few sort of highlights of where I think this has been really interesting. I think the title is maybe a bit too grand. I apologize for that. I think there are many good things, but there are also some big questions. So let's get going. Just a bit of motivation. I mean, this comes from essentially the need or want to have sustainable ways of writing our applications. There are many ways. We don't have the manpower or the resources to sort of do big ground-up rewrites and maintain our completely own software stacks at CSCS. We're there to sort of support scientific applications, and we want to find what are going to be ways that we can write these applications, long into the future. But that's going to be able to leverage actually the communities and other people's work, while at the same time allowing us to contribute to these things as well. So luckily, I think in this room, I don't need to convince you much that CUDA HIP are maybe not the best way to write these things. They have their vendor-specific APIs, the sort of compiler-based pragma, directives-based options are tied to compilers. They can do some good things. You can get quickly started with them. But I think again, in terms of sustainability and maintainability, they can be very difficult alternatives. SYCL kind of had the promise of being an independent thing, but I think nowadays we can count it as essentially the Intel API, in the same category as CUDA and HIP. And then we have things like Kokkos, which I think does very many things right. In the past, I've had this slide where I had a red cross on Kokkos as well, and it's not because I don't like Kokkos, and I had to upgrade it to a question mark for this talk. It does many things right, but I think we can still do better, and I think this is also a sort of common path that Kokkos is going towards with the standardization effort. So I don't think this is in competition. So what if we could use standard C++? We get a lot of benefits from this. This is, we get a common set of sort of vocabulary to use in our programs, available in standard libraries. It lowers the barriers for people actually picking these things up. And as a function of that, you start kind of talking about interoperability. I think you wouldn't really think twice about having another library that, is giving you a std vector, and you start questioning yourself, oh, should I really be using this because it's using std vector? No, because it's always there. And I think finally one big thing is that there is a really large community outside of the HPC world as well, especially within the C++ community that's not here. And I think there's a lot of work that we could benefit from there as well. For the interests of this talk, I'm going to ignore a lot of other things as well. This does not mean that at CSCS or in general we should be ignoring these things. But when we stay within the C++ world, I think the standard has a lot to offer. Right. So then we get to std execution. Well, in the spirit of sort of sticking to other people's work and building on top of that, I think the P2300 proposal, which proposed std execution, does a really good job of explaining why we actually need this. I'll just highlight a few things. The first thing is that the concurrency primitives that we have in C++, or had until now, are really primitives. They're very low level. They're hard to use right. I hope not many of you would dream of sort of exposing those to users, asking users to create std threads or even, std async and std future for their parallelism, because they're both inefficient and can be hard to use right. And then there's a big other part which is about portability and really heterogeneous execution, which the standard did not really care about at all until now. So to basically tackle this, there's a few key features that std execution proposes. So these are terms that you will hear. Don't I have 20 minutes? No, but I have 20 minutes in total. I have 10. Did you see the schedule? I'm not going to be done in 5 minutes. I'm sorry. Hey, good. You got me worried. Right. Yeah, that would have been tight. Good. So schedulers, senders, receivers. There's also a thing called operation states. But most importantly, a set of customizable asynchronous algorithms. These are like the core of what makes std execution. And I'll have a brief overview of those next. So this is in C++26, more or less. It might see small changes, but the bulk of it is going to be there. And I think you can count on it being there in 26. On top of that, there's a nice package manager called SPAC that you can use to install a thing called std-exec, which is the reference implementation. This is from NVIDIA. If you want to get started, I would recommend starting there, though there are many other implementations as well. Right. So I more or less covered this already. Just in case you're confused, you've heard the word executors. This is essentially it, but they've changed the names in between. Sender-receiver is also the same thing. I like to call it std execution just for the whole thing. But if you're talking about the details, you might get to sender-receiver. And if you go to details, people might disagree with calling it executors, because it used to have a different meaning. At a very high level, you get the schedulers. This is essentially what you use to target a specific execution context, meaning a thread pool or CUDA, NVIDIA GPU, AMD GPU, et cetera, et cetera. This is a lightweight handle, so you can copy it around, and it's just sort of a reference to that execution context. Then on top of that, you have senders, which, if you've heard about futures before, they're essentially the same thing, just better. They're a generalization of that same model. And on top of that, you then have the algorithms. So this is actually a snippet from the Kokkos backend that is using sender-receiver. It's using some outdated algorithms, so transfer is no longer called transfer, and ensured starter has been removed. But they're still there and can be used. And I would actually argue that the algorithms are really what makes std execution kind of unique compared to previous approaches. The past proposals had a closed set of algorithms that you could use with futures, or with the executors, rather. And this proposal comes with an initial set of algorithms, but this is essentially user extensible. And there's no special power with these algorithms. They're not, able to do anything that you couldn't do as a user. The underlying sender-receiver model is still what enables you to write these things. So in the most general case, you can write sort of arbitrary DAGs of work. There's some for bulk execution, for joining graphs, et cetera, et cetera. Right. Bit more about std execution still. A few things that make it different from previous proposals. Lazy execution is probably the biggest one. And this is for efficiency. Futures typically tend to be eager. But this adds a synchronization step, because if you want to attach a continuation to one of those futures, you don't know if that thing has completed, and you end up at least dealing with atomics, if not locks, in those cases. And the second thing that lazy execution gives you is that you can sort of build up these bigger graphs of work, just as a description of work, and do one big allocation for them. And this also brings some performance advantages. That doesn't mean you can't do eager execution. It's just that you opt into it when you deem that it's OK to do so, when it's OK from the cost perspective. You also get explicit transfers between execution contexts, which is very nice for actually customizing. How do you go to a CUDA execution context, and how do you come back from it, and things like this. But I won't have time to go into that. error and cancellation are separate from the value channels, which I think we don't really see much in the HPC world because, errors and things like this, we kind of just let the program crash most of the time. But I think in terms of robustness, this is actually a very nice design. And last but not least, I talk a lot about asynchrony, but this proposal is not only about that, because you can also do synchronous execution. So there are in-flight proposals for having, for example, the parallel algorithms just accept a scheduler. And so you get the whole spectrum of kind of synchronous execution to small-scale asynchronous execution where you just overlap things to full-on like task-based programs. All right. Now I want to highlight 3, in my opinion, interesting use cases that we've had with std execution. 2 are in a linear algebra library, and then the last one is actually involving Kokkos, which many of you have heard about, I think. So the first one is in a library that we developed at CSCS called DLA Future. It's a task-based linear algebra library that's targeting a few GPUs. It's using MPI for communication. And the goal is really to have a distributed eigensolver for GPUs. And we've got it integrated into a few electronic structure packages, CP2K, Sirius, and ELSI. And in many cases, we beat, for example, cuSolver MP, which is obviously only for CUDA. On AMD, there is not really an alternative for distributed eigensolvers. And ELPA is the other competitor, and there we also beat them in many configurations. So the problem we have here, this is a full-on task-based program, and we essentially split up these matrices to schedule operations on them, and we need to ensure that these gems and triangular solves are going to be in the correct order. Now, how do we do with this with standard execution? So we came up with this abstraction called async read-write mutex. And this actually started as something that was specific to DLA Future. It was a sort of ad hoc thing where we were managing promises and futures. And then over time, we realized that actually this is quite a nice abstraction that is much more general than what we're doing at the moment. So what it gives you is essentially the async part is that all your accesses to this thing protected by the mutex, you get those through senders. So you get a sender, and then when that thing gets scheduled, you know that you've got access to that value. And then we can do the read-write. You can do read-only access, which is concurrent, or read-write, which is exclusive access. And then we essentially put this on top of all the different blocks in a matrix, and you can access them together in different tasks. And essentially, the queue behind this will make sure that things get scheduled in the correct order. So I'll note, again, I think this is nothing magic. This is something you can do in other places as well. The key is really the sender interface, because that is the glue that means that you can use this with other libraries as well. You can use it with all the algorithms that are in std execution. You can use it with custom sender adapters that come from other libraries, because they all use the same sender-receiver interface. I'll move on in the interest of time. One other thing we've worked on also in the context of DLA Future is MPI integration. Usually the competing libraries, so Scalapack is probably the biggest equivalent package that does this. They're very MPI focused. The distribution of the matrices will use Black's grids and things like this. So we wanted to really focus on MPI and see what minimal integration we can do with MPI in DLA Future and with std execution. So in general, obviously, asynchronous MPI is great. You can do stuff like this. You can overlap compute and communication, but it is quite ad hoc. And this is an MPI-specific interface, right? This is not going to work with anything else. If you want to wait for other things, if you want to do this in a task, you have to modify the MPI implementation to make that work. Especially then when you start mixing this with asynchronous CUDA kernel launches. Now you've got MPI waits and CUDA event synchronize, two completely different ways of actually waiting for things to finish. So what do you do instead? Well, obviously you can hide this behind the sender interface, which is much more uniform and again interoperates much better with other libraries. So we've got a thing called transform MPI, which is a sender adapter. It takes a sender and gives you a sender. And then we've got a similar thing for CUDA as well. Really, it doesn't matter what sort of asynchronous MPI. If you have a way of getting callbacks or some sort of notification mechanism from your asynchronous library, you can hide it behind a sender interface. Right. And I didn't mention this, but so the async read-write mutex, we actually also use it for ordering MPI communication because you want to make sure that that's done in the right order. Just a very quick overview. This is one of the things we've done with Transform MPI. The nice thing about this is we can sort of hide we can hide implementation details behind this API. I won't go into details, but there's a lot of variations you can do on how you do this MPI integration. So we've done some work on experimenting with should you do polling on a separate thread? Should you be spinning on the same thread? You might get lower latency. Should you do both the MPI request and the continuation inline, or should you do that in a new task? And all of this gives a lot of combinatorial options. But essentially, this is all stuff that we can hide. This all fits behind the sender-receiver interface. Right. And then I get a few minutes for Kokkos and HPX in a library called OctoTiger. This has been mentioned already, so I won't talk too much about that. But I would just want to give you an overview of how the Kokkos HPX integration actually looks. So at the bottom of this is actually HPX itself. It's got a threading runtime. And then Kokkos sits on top of that because Kokkos has an HPX backend which is using the HPX runtime. Now HPX exposes a bunch of futures, not senders, to some of these runtimes, CUDA, HIP, and SYCL. But this is something that I think will be updated in the future. That was the backend. Some nice things here that I want to highlight is that it's much easier to optimize this sender-receiver interface. This was written in the past using parallel algorithms in HPX, and it worked well as well. But because of this sort of lazy building of the graph, it actually ends up being much more efficient, and we were able to reduce overheads actually in the HPX backend because of this. Another thing is that senders and futures, you can convert them between each other, so you get very nice interop. On top of this sits a thing called HPX Kokkos, and now I won't go into much detail because I'm running out of time. But essentially, this is what allows this application OctoTiger to do a kind of gradual transition. They were, piecewise porting kernels to Kokkos. This was an application that was already using HPX, and they could start basically doing asynchronous launches of Kokkos work, but getting futures to those things. The last point I want to make, I think there are two important things. One is that all this kind of interop makes it very easy to gradually transition a program to this. So you can actually choose many different paths, and they will all work in the same program. And I think this is a really important story is for the interop working group, and in general for HPSF, I think something that people should be looking at because it's a good way of writing applications. The second thing is that because of the futures, I hope this is something that will move on to use senders more, because currently this is tied to HPX's futures. And if you could move this to actually using the more generic senders, you'd get better interop with other libraries. All right, I'll just leave this up there, and if you have any questions, I'm happy to take them. Thanks.
Okay, we do have some time for questions.
Hi, Michael. Thanks for the presentation. So you have mentioned the mutex in the context of DLA Future and the MPI interop.
Yeah.
Can you maybe elaborate on that? It seems that it's an additional synchronization point which might be orthogonal to the initial idea of queuing in work, which might defeat the purpose of the structured parallelism that we kind of envisioned.
It is, yeah. So I didn't go into detail for this. I think in our use case it works really well, but this is one of the downsides. So it basically creates an implicit graph of dependencies next to the tasks, and I think it depends on your application whether this will work well or not. In our case, I think it worked really well because it lets you write actually code that looks kind of like sequential code, and it lets you sort of this async read-write mutex will take care of, if you're calling this thing in order, the mutex will make sure that those things actually run in order. But I agree. There are cases, I think, where more explicit synchronization is probably nicer. Yep.
I think we could do one more question while the next speaker is setting up.
Oh, hi. I have a question.
Yep.
Thank you. Great talk. I wanted to ask about how this async read-write mutex might interact with the concurrent queue proposal. Could you comment a little bit?
Yeah, it's a very similar idea, I would say. It's a slightly different interface, but it's essentially, it's very much the same idea in the sense that you're just trying to give access to various resources. They will work just fine together. So if you do a when-all on something from a concurrent queue and the async read-write mutex, they'll be just fine. Essentially, this is like a variation of it where we impose certain constraints. We relax it so that you can have concurrent access in some cases, but in principle, it's the same idea. Yeah.
Cool. Thank you.
Yeah.
All right. Do you think you need more time
to
set up? Okay. He will need a second to set up, so we can do one more question if we have one.
I'm here.
Yuchi?
Yeah. Oh, yeah.
Thank you, Randy. How do we integrate the Kokkos platform into your standard task graph?
Is Martin here? There you are. So there is some work already. So one of the points in my conclusion is you can do kind of two-way. You can either treat Kokkos execution spaces as schedulers. This would be interesting, and this is something that Martin and his student have been working on, so I suggest you go talk to him. You could also imagine the other way around. You take a std execution scheduler and put that behind a Kokkos execution space. And in general, so the HPX execution space currently exposes also senders, but it's not general yet, so that you can just take any of the execution spaces. But I would say talk to him.